So this problem actually wraps up 3.5. And if we have a 100-gram ball rolling off a table and landing 2 meters from the base of the table, 200-gram ball rolls off the same table with the same speed. How far does it land from the base of the table? Okay, the question really is what's the difference between a 100-gram ball rolling off the table and a 200-gram ball rolling off the table? Because the speed is the same, gravity is the same, the height off the table is the same. Everything is the same except for the fact that we have a 100-gram ball and a 200-gram ball. So what is it? Well, what you need to realize here, and something that we haven't quite talked about, is the fact that in our kinematic equations, so if I go back to the kinematic equations, here they are. Nowhere in these equations do we talk about mass. There's no m anywhere. So that means it doesn't make any difference what the mass of these balls that are rolling on the table is. 100 grams, 200 grams, 500 grams, 1,000 grams, doesn't matter. Okay? So if that's the case, then who cares if they're 100 grams or 200 grams? Okay? They are rolling off the same table. They are using the same gravity. They have the same speed. So how far do they land from the base of the table? The answer is the same distance. 2 meters from the base, both cases. The answer is D. That's a very important thing to understand. Because gravity acts the same on everything, the mass does not matter. So, the same is true for rolling an object. Okay? The horizontal velocity is the same, so therefore the horizontal distance traveled will be the same. Because the vertical distance traveled is the same. Because the amount of time it takes for everything to fall, the same distance, is the same time. Okay? So hopefully that was understandable for you. It's a concept that's very tricky to get your head around, but once you understand it, it's kind of obvious. Okay? So the next problem is section 6. So this is 3.6 now. Projectile motion, we're solving problems. All right, so 3.5 was sort of introducing you to the concepts of solving problems with projectile motion, motion in 2 dimensions. Now we're actually solving problems. Okay, so actually putting it into practice. So the sport of dock jumping, dogs run at full speed off the end of a dock that sits a few feet above the pool of water. The winning dog is the one that lands the farthest from the end of the dock. So if we just think about that for a second, what is the only controlling factor here? If gravity is the same, the height of the dock is the same, and so on, the only controlling factor is the speed of the dog. Okay? So if the dog runs at 8.5 meters per second, which is a pretty typical speed for the event, straight off the end of a dock that is 0.61 meters, in other words 2 feet, which is the standard height, above the water, how far will the dog go before splashing down? Okay, so what do we do? Well, we're going to need to work with both aspects of the projectile motion because this is a projectile, even though it's a dog. We are moving horizontally and vertically, so that makes it a projectile. And the only thing acting on this dog is gravity once it gets out into the air. Okay? So we have to consider both x and y direction motion. And then remember that the thing that links us to the x and y motion is the change in time. Okay? So we need to go back to our kinematic equations of motion. If you don't remember them or if you don't have them in front of you, here they are. Kinematic equations of motion. So we have our vertical motion equations for free fall, okay, on the left-hand side, and our horizontal motion is uniform motion because there's nothing acting on our horizontal motion. It's a constant velocity, okay? So we need to come up with the horizontal velocity, and then we can use our x sub f equals x sub I equation. Once we have that, then we can come up with our change in time, and then we can use that change in time in our free fall, or vice versa. Okay, so now we come back over here, and we have some information that's given to us. Okay, now we might draw a picture. That's a good idea. So we draw, here's our dock. Okay, now we'll maybe exaggerate so we can see a little bit better. Okay, now here's our dog. Awesome picture of a dog, right? Jumping off of the dock. Now the dog is basically just running straight off the end of the dock. Okay, that's what the problem tells us. So we run straight off the end of the dock. And then of course gravity is going to pull us down, right? And that's where the two-dimensional motion part comes into play. So we run straight off the end of the dock. That means our initial velocity is directly horizontal, okay? So that's your v sub I. Now, as time goes on, of course, we're going to start to gain a vertical component to the velocity, but initially we have just a horizontal component to the velocity in the x direction. So we should set up axes. We have x direction, y direction, positive is up. Okay, positive x to the right, positive y is up. Okay, so that's kind of the idea of what's going on. Now, the dog runs at 8.5 meters per second. What is that? So that's your velocity in the x direction, and that is your initial velocity in the x direction. Okay? Now, because the x direction velocity is going to be unchanging, that is also your x direction velocity final. Okay? It's unchanging. So this is 8.5 meters per second. Okay, now we have the dock is 6.1 meters up. Okay, and we're going to use the 6.1 meters, not the 2 feet. Okay, they're just helping us out visualizing what 0.61 meters is. So what are we going to call that? Well, that's in the y direction. So we're going to call that y initial is 0.61 meters. Now, the dog, if we call the origin here, okay, there's the origin, then the dog is up at 0.61 meters, and that's why it's y sub I. Okay, so what's y sub f? Well, according to our picture, y sub f would be what? It's landing in the water. Okay, so y sub f would be the height of the dog when it hits the water, which would be 0 meters. Okay, now what's x sub I? The position of the dog in the x direction when it leaves the dock. If the origin is right where I drew it, well then x sub I is 0 meters. And what's x sub f? Well, that would be this distance here to where it lands, okay? And that is what we're looking for. How far will the dog go before it splashes down? That's what we need to find, okay? So that is what we need. X sub f is what we need. Okay, so now what else do we know? Anything? What about our accelerations? Do we have an acceleration in the x direction? The answer is no. This is uniform velocity, uniform speed in the x direction. So we have no acceleration. That's meters per second squared there. And acceleration in the y direction. What is that? And that's gravity. So we could say negative g here, or we could just say negative 9.8 meters per second squared. It's negative because it's going against the positive y direction. Okay? So that is all of the information that we know. Now, we need to think about our kinematic equations of motion for 2 dimensions. How can we use these pieces of information with our kinematic equations to come up with something that's going to help us relate these x direction motions and y direction motions together. Because the one thing we don't have here is time. Actually, I could write something down for time. I know initial time. T sub I is 0 seconds. I just don't know T sub F, okay? So if I figured out the final time, that would give me T sub I and T sub F, so I could figure out delta T pretty easily, all right? And that's kind of a hint. I can figure out T sub F. I can figure out T sub F by using free fall, because I know the height of the dog to start. Because of gravity, I can figure out how long it's going to take the dog to hit the water. And once I have that, I will have my T sub F for both the y direction and the x direction. And once I have my T sub F for the x direction, let me go back to the kinematic equations. Once I have my T sub F for the x direction, I'll be able to use my delta T right there and be able to find my x sub F. Okay? Now, since I know that I need to find my T sub F, let's look at the kinematic equations for the vertical motion. I don't know my final velocity, so this top equation probably isn't going to be any good here. But let's look at the bottom equation. Y sub final is 0. Y sub initial is 2 feet, whatever that was, 0.61. The velocity in the y direction initial was 0. It was not falling. The dog was not falling down initially. So that's going to wipe out that term. And then we have 1/2 gravity, we know. And then delta T is what we're looking for. Okay, we're looking for delta T, by the way, is T sub F minus T sub I, and T sub I was 0, so really we just have T sub F sitting there, okay? So that's the equation that we want to use. So let me go back now to the problem that we're working on, the problem at hand. And the formula that we want to use first is this free fall position equation. So I'm going to write it down. So we have y. The more you write these equations down, the more quickly you're going to remember them, by the way. Y sub F equals y sub I plus see, now I don't remember it. Okay, and then I'm kidding. It's v sub y, velocity in the y direction initial. And I'm being specific about that because of the fact that I could be talking about the velocity in the x direction. So I want to say the velocity in the y direction initial times delta t. And then it is going to be minus, or it could say plus, but we're going to say minus 1/2 g. And g is just gravity. And we know that gravity is 9.8. So minus 9.8 is what's going to end up being there. And that's why I said you could say plus, but then I would write a instead of g. Delta t squared. Okay, now we know that there's some things here that are going to be 0. So let me change my colors here so I can make some things 0. We know that the position final is 0. So 0 there. The initial position, we know, is not 0. Velocity in the y direction initial, there was no velocity in the y direction initially, so we're going to call that 0. And that wipes out the whole term. And that is good. So let's go back now. I'm going to change back to blue. Okay, so we have 0 equals y initial. That term is gone. Minus 1/2 g. And then delta t I'm going to rewrite as, so change in time is time final minus time initial. But we know that time initial is 0. So this is just going to be time final squared. Okay, now we know the initial time, we know the initial position, we know gravity. We're looking for the final time. So I'm going to add the right-hand term to both sides, and that gives me 1/2 g t final squared equals y initial. Okay, that just keeps my terms positive. Now, I want to solve for time final, so I'm going to multiply both sides by 2. So now I have 2y initial on the right-hand side. I need to get rid of the gravity, so I'm going to divide both sides by g. I need to get rid of the squared, so I'm going to square root both sides. And now I have time final. Okay? So now I can plug in my stuff. I have square root 2 times y initial. Y initial is 0.61 meters divided by gravity, which is, and notice that now gravity is positive here, okay? That minus sign became positive, and now it's 9.8 meters per second squared. So now do a unit analysis here. Meters divided by meters is gone, and then the 1 over second squared becomes second squared on top. The square root of second squared is seconds, so this is just seconds, which is great because it's time that I'm looking for here, and so I have seconds as my units in the answer. So when we do that calculation, what do we get? Oh, I wind up with 0.35 seconds. Okay, so it takes the dog 0.35 seconds to hit the water. All right. Now, that's not the end of the question, though. The question is, how far will the dog go? So now we can go back to our kinematic equations. Let me bounce back to those equations. Where are they? There they are. Okay, so now we have x sub f equals x sub I, which we know already is 0, plus v sub x sub I, we know that already, times delta t we just found. So we have everything in that equation now. We can find x sub f. Okay, so we go straight to that. X sub f, I'm going to write down the whole thing, equals x sub I plus v sub, oh, see, now I forgot. I actually did forget this time. Oh, that's not where I want to go. So, here. Okay, v sub x initial delta t. So, v sub x initial delta t. Okay, so we know that x sub I is 0. And now we have x sub f equals just the v sub x initial, but that's known, and it is 8.5 meters per second times the delta t that we just found, which was 0.35 seconds. Now, when I do this calculation, I would use my calculator answer, not the rounded answer that I just found. And when I do that, I wind up with, with significant figures, a 3.0 meters is the answer. So that dog flies 3.0 meters through the air, which is pretty good. Okay, so that's how you do that problem. You're using both horizontal and vertical motion tied together by the delta t. Okay, and remember the delta t is t sub f minus t sub I. All right. So your tips for projectile motion problems. Okay, make some simplifying assumptions. Whether the projectile is a car or a basketball, the motion is going to be the same. Okay, you launch a car or you throw a basketball, it's still going to be a projectile, and you're still going to be dealing with x components and y components. Draw a visual overview, so draw a picture. Okay, draw a pictorial representation showing the beginning and ending points of the motion. Okay, then you establish the coordinate system with the x-axis horizontal and the y-axis vertical. In this case, you know the horizontal acceleration is going to be 0, and the vertical acceleration is free fall. So a sub x, the acceleration in the x direction is 0, like we just saw, and the acceleration in the y direction is negative g. G is 9.8 meters per second squared, so it's negative 9.8 meters per second squared. Okay. Then draw a vector representing the initial velocity All of this should be familiar to you because we just did all of these things. And find its x and y components in terms of the initial speed and launch angle. So in the last problem, the initial speed and launch angle, it was just a horizontal launch, so we didn't have any of that. But we will. We'll do a problem where the initial speed and launch angle, we have an angle of launch, okay? Define symbols and write down a list of known values. We did all that, okay? We made an inventory of stuff that we knew, and we found the thing that we didn't know, and then we worked towards sort of identifying with our kinematic equations what it was that we didn't know and how we were going to get there. Okay, identify what the problem is trying to find. It is important that you do that so that you have a direction to go. All right, if you don't do that, you're just going to sit there and kind of fumble around and then eventually drown. You're just not going to know what to do. So solve using the kinematic equations for projectile motion, and here they are one more time. So the horizontal ones are these guys on the left, and remember that v sub x final is the same as v sub x initial. They're both the same and they are constant. They will not change throughout the motion of the problem. For vertical, that's not true. We're going to have acceleration in the vertical direction, and those are your two equations right there. All right? So you need to know these. Work with them, write them down a lot so that you learn them and remember them. You're going to have a note card for the test. Make sure that these are there and that they're in an obvious location. And also remember that you could say this too. Acceleration in the x direction equals 0. You could say acceleration in the y direction is equal to negative g. Or you could say equals negative 9.8 meters per second squared. Okay. I didn't put them there because it's a given. We know that, or we should know that. But if you want to write them down so that you know that, well, then there you go. Okay, so moving along. So we have a soccer free kick. The player kicks a stationary ball toward the goal that is 18 meters away. Okay, he kicks the ball at an angle of 22 degrees from the horizontal at a speed of 23 meters per second. How long does it take the ball to reach the goal? How far off the ground is the ball when it reaches the goal? So we have two questions to answer here and just a bare minimum amount of information. But we can answer both questions with even just this little amount of information. So what do we do? Well, the first thing we do is we're going to draw a picture to set this problem up, and then we're going to make an inventory of the stuff that we have, that we know, and then the stuff that we don't know. Okay? So first of all, set up like maybe axes with an origin and set the ball being kicked at the origin. Okay, that's the first thing I would do. So I have axes. Okay, this is the x direction, this is the y direction. And now I'm going to kick this ball. So I'm going to change colors here. Now I'm kicking this ball. Here we go. It's at an angle of, ooh, that was really bad. Let me fix that because this is terrible. Fix, go away, go away. Okay. It's at an angle of, oh, that was no good either. Okay, so I'm going to do something a little bit different. Erase. There we go. Okay, so I'm going to do this. Change colors. 22 degrees minus 90 would be 68, right? Okay, so that's 22 degrees. I cheated a little bit, but at least it looks better. Okay, so that is my kick. We have 22 degrees sitting in here. Okay, angle of 22 degrees with the horizontal. And now it has a speed of 23 meters per second. So that means that this vector right here, we can make it a vector, has a length of 23 meters per second. Okay, that's its speed. I'm saying that it is a vector and I can call it a length of 23 because I'm not talking about its direction. Okay, When I don't talk about its direction, it now has a speed instead of it being a vector. So once I put the direction of 22 degrees on it, now it's a vector again. Okay. So now, how long does it take the ball to reach the goal? Well, the first thing we need to do here is start making an inventory of stuff. All right. So overall, this is the vector. But this doesn't do us any good. We need to break this thing into components. We need a vector in the x direction. So we need the velocity in the x direction, initial, and we need the velocity in the y direction, initial. Okay? So break this vector into components right now. How do we do that? Well, we need to remember that we're dealing with a right triangle sitting here, okay? And we have this 22-degree angle sitting there. So if I want v sub y, that's going to be this side, the opposite side, divided by the hypotenuse. And we know the length of the hypotenuse is 23. So opposite over hypotenuse. So that would be sine. So I have v sub y initial is, v sub y initial is the opposite side, right? That's v sub y initial over the hypotenuse, and that would be sine 22 degrees. So if I multiply both sides by 23, I will have 23 sine 22 degrees equals v sub y initial, okay? And it's just a matter of calculating that. And then for v sub x initial, it's the same idea, except now it's going to be cosine. So if I multiply both sides by 23, I'll have 23 cosine 22 degrees. And when I multiply that out, I'll have v sub x initial. Okay? So we need to do those two things. And when we do, we get v sub y is 8.6 meters per second. V sub x initial is 21.3 meters per second. Okay? Now you can kind of check yourself by drawing an accurate looking sketch. V sub y should be significantly smaller than 23, and v sub x should be fairly close to 23. Both should be less than 23 though, and they are. So it seems like we did a pretty good job here. Okay? So now we have those components. We have to do that because we're going to need to analyze the x direction motion and the y direction motion separately, but at the same time. Okay, so we have to break this into components. Now, what else do we know? Well, we know x sub I, the initial position, is 0 meters. We know x sub f, the final position, is 18 meters away. We know y sub I, it was on the ground, so that's 0 meters. And we know t sub I, we can start time when the ball is kicked, that's 0 seconds. We know theta, it's 22 degrees. Anything else we know? What don't we know? I think we know everything. We have written down everything we know. What don't we know? We have y sub I. We don't have y sub f. Okay? It's the questions here. Say how far off the ground is the ball when it reaches the goal. That's y sub f. We don't know that. And we also don't know how long does it take the ball to reach the goal. That's t sub f. Okay? Those are the two things we're looking for in this problem. So now we know what we know, and we know what we don't know, and we have a good picture, and we've broken the vector into components. We're ready to go. We have our kinematic equations for two-dimensional motion, We can work with that. We just got to figure out our delta t. We know t sub I is 0, so that's going to simplify delta t to just t sub f, and t sub f is one thing that we're looking for. So we have to solve for t sub f at some point, okay? So how do we do that? What do we need to do? Which formula do we need? Well, if I go back to my kinematic equations, knowing what I know and what I don't know, see, I know I have x sub f and x sub I, okay? Since I have both of those, and I know my velocity in the x direction, okay, 21.3 meters per second, and it's going to stay 21.3 meters per second the whole time. If I go back to my kinematic equations right here that are at the bottom of the page now, for horizontal motion, I need x sub f, x sub I, and the velocity in the x direction. And if I have all that, I can calculate delta t. That's perfect. That's exactly what I need here. All right, so let's go back, and we can use that equation. So I'm going to change colors again, and let's use x sub f equals x sub I plus, really it's the velocity in the x direction because the velocity doesn't change, delta t. Okay, now x sub I is 0, and I'm solving for delta t. So I have x sub f over, if I solve for delta t, v sub x, the velocity in the x direction, which is unchanging, equals delta t. I can substitute that stuff in. X sub f is 18 meters divided by v sub x, which is the 21.3 meters per second. Meters divided by meters is gone. 1 over seconds becomes seconds. So I have time is seconds, which is great. And the answer is 0.845 seconds. Now, how long does it take the ball to reach the goal? That is an answer, so I'm putting a box around it. Okay. Now, how far off the ground is the ball when it reaches the goal? Now we're talking about a y. This is a yf situation. So I need a kinematic equation that deals with a y. Okay, y sub f. Well, that's a pretty obvious one in my mind anyway, because the only kinematic equation for vertical motion that has a y sub f in it is that y sub f equals situation. Okay, so y sub f equals y sub I, which was 0, plus velocity in the y direction initial, which we know already, we calculated it, delta t, which we know, we just calculated it, minus 1/2 g, which is 9.8, and then the delta t squared, we just calculated it. So we know all of that equation now. So we can calculate the y sub f right now. So I'm going to go back to the problem, and I'm going to write the equation down. Y sub f equals y sub I, and because it's late and my brain is not working, plus Vy delta t plus velocity in the y direction delta t minus 1/2 g delta t squared. Okay, and like I said, velocity, not velocity, y initial is 0. Now velocity in the y direction, we know, we can start plugging everything in. So we have y sub f equals, velocity in the y direction we calculated was 8.6 meters per second. Delta t we just calculated, 0.845 seconds, minus 1/2 g, which is 9.8 meters per second squared. And then delta t again is 0.845 seconds. This is squared. Type all that in your calculator, and we'll see what we get. It winds up being 3.8 meters is your answer. So the ball is 3.8 meters off the ground. I don't know much about soccer, but I'm guessing it did not go in the goal. I think it probably went over it. Okay, so that's how you do that problem. All right, so now the range of a projectile. Okay, so for a projectile, the initial speed and the launch angle are the two variables that determine the range. At a very small or very large angles, the range is small. Range is how far does it go from where you launched it. Okay, so if I have a very small angle, so let's say I'm sitting here, okay, with some sort of a cannon or something, okay, if I launch it at a very small angle, it's not going to go very far. If I launch it at a very large angle, it goes way up into the air and then it comes down and it just doesn't go very far horizontally. Okay? It's amazing drawing. If you throw a ball at a 75-degree angle, the ball does a lot of up and down, a lot of up and a lot of down, but it doesn't go very far. Okay? If you throw a ball at an angle of 15 degrees, the ball won't be in the air very long and it doesn't go very far. Okay? So the just right case for the ball to travel the farthest is to throw it at 45-degree angle. That's where it will go the farthest. Okay? And if you did the simulator that we were working on the other day, you saw that probably. Okay? If you played around with it enough, you probably were like, well, I wonder how I can make this go the farthest. And it was 45 degrees. Okay? However, for real life projectiles like golf balls and baseballs, the actual optimal launch angle is less than 45 degrees because of air resistance. So in the real world, like if you're a golf player, you would not want to launch your golf balls at 45 degrees because there is air resistance out there. You'd want to launch it a little less than 45 degrees to get the optimal distance. So anyway, for small objects traveling at high speeds, air resistance is critical and can't be ignored. So for things like golf balls, you would have to take air resistance into account. But we're not doing that. We're basically ignoring air resistance. So we can. I just wanted to bring it up. It's important to talk about. It's important to keep in mind that for these problems that we're working on here, we are simplifying the math so that you can focus more on the concepts. Okay, that's the idea. So, baseball player is taking batting practice. He hits two successive pitches at different angles, but at exactly the same speed. Ball 1 and ball 2 follow the path shown. Which ball is in the air for a longer time? Assume that you can ignore air resistance for the problem. So, ball 1, ball 2, or both are in the air for the same amount of time. Think about it. The answer is A. Ball 1 is in the air longer. And the reason is this. Yeah, ball 2 went farther. Ball 1 didn't go as far. But that's not what we're talking about here. We're talking about which one is in the air longer. And when we're talking about duration in the air, we need to be looking at the vertical component of velocity. Okay? Because ball 1 has a greater vertical component of the velocity, we have a longer amount of time that ball 1 is going to be in the air, simply because the only thing acting on ball 1 is gravity. So it's going to take ball 1 longer to come to a stop vertically than ball 2, which means it's going to take ball 1 longer to come back down to the ground than ball 2. Okay? Ball 2 goes farther, but ball 1 takes longer to come back down to the ground. And that's what the question is asking. So the answer is A, ball 1. that is the end of section 6. So at this point, you're now able to do the problems for homework for section 6.